In this recording, we're going to be looking at this particular scenario. I want to let R be a finite ring, and I want to let S be any ideal of R. Now, because S is an ideal, we know that R mod S, under its coset addition and coset multiplication, is a full-fledged ring. And my question is, what can we say about this quotient ring? So what, if anything, can we say about R mod S? Now, a throwaway comment, it seems like in this kind of a situation that R mod S ought to be a finite ring. So I want to kind of go beyond that. And one of the things that I want to do is I want to review something that we covered several videos ago. We know something about finite rings and their subrings, and that thing is called Lagrange's theorem. So I want to review Lagrange's theorem. And Lagrange's theorem says that if I have a finite ring, so let's let R be a finite ring, and if we let S be any subring, we don't even need an ideal here. So S is just any subring of R. Then, the first thing is, the simplest thing is that the order of S divides the order of R. But it turns out that we were able to show something even more special. And in fact, we were able to show that the order of R, the number of things inside the ring R, was equal to the index of S in R times the order of S. And it's important to remember that the index is just the number of distinct left cosets of the subring R. And this particular notation is often called the index of S inside the ring R. And so that's what Lagrange's theorem said. Now, the situation that we have is that S is an ideal, but I want to remember that if we have S is an ideal in a finite ring named R, well, all ideals are subrings. So then I know that S is also a subring of R. And so I do know that Lagrange's theorem applies. In other words, the number of things in my finite ring R is going to be equal to the index of S inside R times the order of S. And this is again where the index is nothing more than the number of distinct left cosets of S inside R. But now I want to think about, what does ideal mean? Ideal, of course, means that R mod S is a ring. And the elements of R mod S are the left cosets of S. And hence, we know that the order of R mod S is nothing more than the index of S inside R. And so what I want to do is I want to substitute this particular fact. I'm going to substitute this particular fact into Lagrange's theorem. And when we do that, this is what happens. So we get the order of R is equal to the number of left cosets, which is just the size of the quotient ring, times the order of S by Lagrange's theorem. Now what this lets me do is this actually lets me solve for the number of left cosets in terms of the order of R and the order of S. So in other words, what we have is that the size of the quotient ring will be equal to the size of R divided by the size of S. In other words, what we have now shown is this particular theorem. So we have proved this theorem. And this theorem states that, the following. Let R be a finite ring and S is any ideal of R. Then the order of the quotient ring R mod S is going to just be the order of R divided by the order of S.